Hi, welcome back to discussion of lecture on WKB approximation. And this would be the last lecture on this approximation method. And the topic of this lecture is the connection formula. So we already discussed the beginning of the connection formula in the last lecture. I will just revise what are the things that we have discussed in the last class. So consider a system, a quantum mechanical system. So quantum mechanical system, its potential characterized by V of x. X is a position. Suppose the V of x is of this particular form, and this quantum mechanics system has a total energy E. Okay, so then this point. Okay, so for the time being, I will put this point as x equal to 0. So this x equal to 0 point is called the classical turning point. Classical turning point. So I can divide the region into two, the region 1 and the region 2. The region in region 1, the potential energy is lesser than the total energy. So that is classically permissible. So hence the region 1 is called the classically allowed region. So in region 1, the total energy is greater than potential energy, and it is called classically allowed region. And in region 2, the total energy is lesser than the potential energy, and which is not permissible classically, and hence we call it as classically forbidden region. Okay, now this is just terminology that we already know. Now what is the WKB approximation? The WKB approximation says that if V of x is slowly varying function, if V of x is slowly varying, then the wave function psi of x can be approximated as, in WKB approximation, it can be written as either in the form of exponential, either it can be written as an exponential function or a harmonic function. Okay, so if the potential is a slowly varying function of position, then I can approximate my wave function of this particular form. So it will be exponential in a classically forbidden region, and it will take harmonic form in a classically allowed region. And those things we have discussed in detail, and we already found what is the form of the wave function. So the exponential form I can write, so WKB wave function. Okay, let it be in classically allowed region, it can be written as 1 by root p of x root p of x into e raised to I by h cross integral p of x dx or p of x prime dx prime plus 1 by root p of x. Okay, I can do some constant b here and some constant c in the e raised to minus I by h cross integral p of x prime dx prime, and the integration is from x prime to 0. So the WKB function will take this form in classically allowed region, that is in the region 1, And whereas in region 2, the WKB wave function takes another form. It will be exponential d by modulus of p of x, the magnitude of p of x into e raised to minus 1 by h cross integral 0 to x, the magnitude of p of x dx. So this would be the form of WKB wave function in the classically forbidden region. So I have purposefully am not included the term of e raised to plus 1 by h cross. The reason is here x can go up to infinity. So if the x can go up to infinity, then positive exponential will diverge, and that will not satisfy the normalization of the wave function. Okay, the convergence of wave function. So therefore I have neglected the positive exponential term. So actually there can be two possibilities in classically forbidden region. There can be negative exponential and as well as positive exponential. So I have neglected the positive exponential term in this particular problem. The reason is here the x is going up to infinity. So if you have some other problem like suppose if the potential is varying like this, then you can divide the region into three: region 1, region 2, region 3. Okay, so then in region 2 I have to add the positive exponential term as well. So depending upon the situation, so here there will be some other term, some f by square root of modulus of p of x into e raised to plus 1 by h cross integral 0 to x modulus of p of x prime dx prime. Okay, so those things we have to include if the problem of this particular manner. Okay, but for simplicity I am considering only one turning point is present in the system, and that would be enough to illustrate the discussion of the connection formula. Okay, so let me remove. Okay, so this is our system. So now remember, this WKB wave function is an approximate solution if the potential is a slowly varying function. And what is the momentum here? If you look at this equation, the momentum p of x equal to square root of 2m to e minus v of x. Okay, now this momentum, what would happen is this momentum will tend to 0 when we approach the turning point. Okay, so near turning point, what would happen is near turning point, so better I will use some other color. So near turning point, the total energy is approximately equal to the potential energy. So then what would happen? This p of x, so the momentum of x would tend to 0. So that leads to the fact that the WKB wave function will tend to infinity, which is not permissible. Okay, the wave function cannot diverge. So this is not permissible. So hence what would happen is I cannot assume the WKB approximation. I cannot consider the WKB approximation for the region very near to the turning point. So I can mark those regions. So very near to the turning point, the WKB is not valid. Okay. So then how we can connect the WKB wave function on the left side and the WKB wave function on the right side? So that will be the question. Now the central region, so this is central region are the region in which WKB is not valid, but I can find the actual wave function near this central region. Now the central region, I will give some other name for it. The central region is also called the patching region. Okay, now I can find the wave function, the actual wave function near the patching region by approximating the potential. Okay, now here in general, I can write my potential V of x. 1 second. V of x, you can expand in Taylor series near the turning point 0, x into V prime of 0, x square by 2 factorial V double prime at 0 plus so on. Okay, so we'll copy this figure. So the potential near the turning point I can expand my potential as this form, the potential at 0 into x into the first derivative of potential at 0 plus x square by 2 factorial, the second derivative of potential at 0 plus etc. Now in the first order approximation, the first order approximation, the potential near the turning point, I can write V of 0 plus x into P prime at 0. So this approximation we already discussed in the last class. Okay, so actually what we have done is this is the linearization of potential. So in the patching region, I can approximate the potential as a straight line. Okay, so I am just neglecting the curvature near the turning point. I can approximate the potential as a straight line. Now this is nothing but the equation for a straight line. Okay, so if the potential become linear, then what would be our Schrodinger equation? So this we have discussed in detail in the last class. So our Schrodinger equation will take the form of Airy equation. Okay, so I will write it. The Schrodinger equation can be written as d square psi by dx square equal alpha cube x into psi of x. Where alpha is a new constant that we introduced. So alpha is given by 2m by h bar square, the first derivative of potential at 0, all raised to 1 by 3. Okay, now this wave function is valid near the patching region, and hence this wave function I will call it as a patching wave function. Now we can change the variable. I can change the variable to new variable z, where z equal to alpha times x. Then the Schrodinger equation will take the form d square psi p by dz square equal z into psi p of z. So this equation is a famous Airy equation. The Schrodinger equation will take the form of Airy equation near the turning point or in the patching region. Okay, now its solution, there are two possible solutions. One is for z greater than 0 and another one is for z less than 0. So for z greater than 0, the asymptotic solutions are, or if z much greater than 0 and z much less than 0, the asymptotic solutions is given by, since it is a second order differential equation, there can be two possibilities. So ai of z written as 1 by 2 root pi z raised to 1 by 4 e raised to minus 2 by 3 z raised to 3 by 2, and next possibility bi of z equal 1 by root pi z raised to 1 by 4 e raised to plus 2 by 3 z raised to 3 by 2. Okay, so this would be the solution of the array equation for z much greater than 0, two independent solutions. Okay, and for z much less than 0, the solutions are the harmonic functions. It is ai of z is given by 1 by, so better I will write in the next page. Okay, so for z much less than 0, this would be harmonic function. So 1 by root pi minus z raised to 1 by 4. The sine of 2 by 3 minus z raised to 3 by 2 plus pi by 4. And bi of z is 1 upon root pi minus z raised to 1 by 4. It will be a cosine function. 2 by 3 minus z raised to 3 by 2 plus pi by 4. Okay, so only difference is one is sine function, other one is cosine function. They are linearly independent. Okay, so these are the possible solutions of array equations. Okay, since we have two possibilities, z much greater than 0 and z much less than 0, so anyhow the wave function psi p, the patching wave function psi p of x or z, psi p of z would be linear combination of both ai and bi. So it can be written as small a into ai of z plus small b into bi of z. So in general, the patching wave function would be the linear combination of both ai and bi. Okay. Now, which ai and which bi has to be used, that depending upon the region. If it is z much greater than 0 or z much less than 0, accordingly, we have to use the form of ai and bi. Okay. So next, what we can do is, okay, so next we can discuss how we can use the information about the patching wave function to connect the WKB wave function in region 1 and region 2. Okay, so let us go to our next slide. So this is not required for us. Better we'll remove it. Okay. So I will redraw our graph again. This was our potential form. and this is our energy E. I've chosen this point as x equal to 0. Now, near x equal to 0, this region we called as a patching region. Okay. Now it is possible to extend the patching region to some more to the region 1 and region 2. So in region 1 and region 2, the wave function is already in the form of WKB form. And in the patching region, it is linearized. The patching region, it is almost a straight line. Okay, now it is possible we can extend the straight line to some more to the left and as well as some more to right. Okay, now I can define a new region here. This new region, these regions are called the overlap region. So there are two overlap regions, overlap region 1 and overlap region 2. So overlap region in the sense that both the patching wave function and WKB wave function is equally valid. Okay, so this region, the central region, is called the patching region, and the region 1, that is WKB, is valid, and region 2, WKB is valid, and in the patching region, WKB is not valid. We have to use the patching wave function. Now we can consider an overlapped region on both sides, in which both the patching wave function, WKB wave functions are valid. Now this information can be utilized to connect the WKB wave function on both sides. So that is the crux of the idea behind the connection formula. Okay. Now in the overlap region, we can calculate what would be the moment. Okay. So in the overlap region, again, the potential can be considered as a linear function. So v of x equal to b at 0 plus x into v prime at 0. Now the potential at x equal to 0 is nothing but energy. So E plus x into v prime at 0. Now in the overlap region, what would be the momentum? P of x is equal to square root of 2m E minus v of x, and that would be root 2m E minus the potential is of the form E plus x into v prime at 0. So this E cancels, and therefore the final result would be square root of 2m into v prime at 0, the square root of minus x. Okay, now root 2m into v prime at 0 can be written in terms of alpha, because alpha is given by 2m by h bar square v prime at 0. Okay, so this alpha is of this form, so therefore 2m v prime at 0 can be written as alpha cube h cross square. So this can be written as alpha cube h cross square root of minus x. Okay, so in the if you look at the region 1, the region 1 are the region with x less than 0, and hence this p of x would be obviously positive. And for region 2, it's x greater than 0, and this would be it will become a complex quantity there. Okay, but obviously I know what is the wave, what are the wave function in this region 1 and 2. Okay, let me go back to that slide. Okay, the WKB wave function in region 1 is of this particular form. And in region 2 of this form. So I think first we can calculate what would be the WK. We can write WKB wave function region 1 by looking at those things. Okay, and I feel we can cut this portion. Okay, so that is not working. So better I will write here. So psi p of x or psi WKB of x is some b by root of p of x e raised to plus I by h cross integral x to 0 p of x prime dx prime plus c by root of p of x e raised to minus I by h cross integral x to 0 p of x prime dx prime. Okay. Now what would be integral x to 0 p of x prime dx prime in region 1. Now this p of x prime dx prime can be written as alpha cube h cross square. If since x is negative, it become root plus x into dx. Or I can write this equal to alpha cube h cross square x raised to 3 by 2 by 3 by 2 x to 0 and hence this integration will take the form alpha cube h cross square 2 by 3 minus x raised to 3 by 2. Okay. I think that's correct. I think I have made a mistake here. So here it is not alpha cube h cross square. It is alpha raised to 3 by 2 h cross, because what I need is square root of 2 m v prime 0. So I have to make the square root there. So I have to make a square root here. So this would be alpha raised to 3 by 2 h cross square root of minus x. So this become two by 3 alpha raised to 3 by 2 h cross x raised to 3 by 2, and there will be an overall minus sign. So better I can write this 2 by 3 times h cross minus alpha x all raised to 3 by 2. So this is the form of integral x to 0 in region 1. Then what would be our wave function in the region 1? I can write 1 by square root of p of x. And what is p of x? P of x is alpha raised to 3 by 2 h cross root minus x. So square root of p of x will take the form h cross square root of h cross alpha raised to 3 by 4 minus x raised to 1 by 4. A raised to I by h cross. The integral can be written as 2 by 3 h cross minus alpha x all raised to 3 by 2, and here the integration constant is p plus c by root h cross alpha raised to 3 by 4 minus x raised to 1 by 4 a raised to minus I by h cross 2 by 3 h cross minus alpha x all raised to 3 by 2. So this is a WKB wave function in the region 1. Okay. Now in the now I can go for the region 2. So this can be written as some equation number. So the equation number, the previous cases also we have to put some equation number. This can be our one of the main equation. This can be equation number 1. This can be equation number 2. This can be equation number 3. And this can be equation number 4. Okay. So next we can calculate the same thing for region 2. Now for region 2, the integration is from 0 to x p of x prime dx prime. Now remember here this momentum would become imaginary, and I have to take just magnitude of this momentum. Okay, so remember the momentum p of x is alpha raised to 3 by 2 h cross square root of minus x. So in region 2, x is positive, so the p of x is imaginary. Okay, so what would be the magnitude of p of x? Magnitude of p of x is simply alpha raised to 3 by 2 h cross root x. Okay, so I have to use the magnitude of p of x prime here and I have to integrate it. So this become alpha raised to 3 by 2 h cross integral 0 to x root x dx. So the final answer will be 2 by 3 h cross alpha x all raised to 3 by 2. So hence the WKB wave function in region 2. Region 2 I can write capital D by square root of the magnitude is equal to h cross alpha h cross raised or root h cross alpha raised to 3 by 4 x raised to 1 by 4 into e raised to minus 2 by 3 h cross alpha x all raised to 3 by 2. So this would be the wave function in region 2. Okay, so previously I have put the equation number 4. Now this can be my equation number 5. Now what is the form of the patching wave function? The patching wave function psi p of x is written as small a into AI of. Okay. So now we can write the patching wave function in the overlap region 2. Okay. So there are two overlap region as we have mentioned earlier. So if you go to the previous slide, I can see here. So this is my second overlap region. So in the overlap region are the region which x greater than 0 or z greater than 0. So in those region, what would be our the patching wave function, WKB wave function, we can connect it. Okay. So I will just see, is it possible to copy it to my new page. Okay, it is not possible. Okay, so I will just redraw it again or plot. Is a form of the potential we have. And this is my total energy E, the classical turning point. And this is my overlap region. So in the overlap region, the AI and BI. So we already know the form of AI and BI. The AI is negative exponential, and BI is positive exponential. So now on the right side, there cannot be any positive exponentials. So therefore, in region 2, the psi p of x, I can write the forms for A into AI only, where AI is given by 1 by 2 root pi alpha x raised to 1 by 4 into exponential minus 2 by 3 alpha x raised to 3 by 2 plus small b, and capital BI will take the form b by root pi alpha x raised to 1 by 4 e raised to 2 by 3 alpha x raised to 3 by 2. Now from this very clear that this term would be 0. Okay, because in so by equating the WKB wave function in the overlap region 2, which is of equation number 5, and the patching wave function of this particular form as in equation number 6. Equation number 6. So by equating the 5 and 6, which implies that the constant b would be 0. Okay, so this would give a straight connection between the coefficients capital D and the coefficient small a. So this should be same, and hence I can write my a equals square root of 4 pi divided by h cross alpha into capital D. And this can be question number 7. Okay, so I've got a connection between small and capital D by connecting the wave functions, the patching wave function and as well as WKB wave function in the overlap region 2. So similarly, we have also identified another overlapping region, so which is your the overlap region 2 or overlap region 1. So here we can consider another overlap region. So in overlap region 1, what would happen is again the WKB wave function, batching wave function should match. So for region 1, what is the form of WKB wave function? That we already written, capital B by square root of cross alpha raised to 3 by 4 minus x raised to 1 by 4 e raised to I by h cross 2 by 3, and this h cross would cancel. E raised to I times 2 by 3 minus alpha x raised to 3 by 2 plus some constant c divided by the same constant root h cross alpha raised to 3 by 2 minus x raised to 1 by 4 exponential minus I 2 by 3 minus alpha x again all raised to 3 by 2. And what would be the form of the patching wave function? So the patching wave function, so here some the constant a into ai times alpha x. Now this is a region 1 is a region with the x less than 0, so it would be sinusoidal here, and hence your psi p, the patching wave function in this overlap region 1, I can write a by root pi minus alpha x all raised to 1 by 4, the sine of 2 by 3 minus alpha x all raised to 3 by 2 plus pi by 4. Now I can write sine theta as e raised to I theta minus e raised to minus I theta divided by 2i, and hence I can write this equal to a by root pi minus alpha x all raised to 1 by 4 e raised to I 2 by 3 minus alpha x all raised to 3 by 2 plus pi by 4 minus e raised to minus I 2 by 3 minus alpha x all raised to 3 by 2 plus pi by 4 all divided by 2i. Okay, I can put some equation number. So in the previous slide, what was the last equation number? Equation number 7. So this can be equation number 8 and equation number 9. So the 8 and 9 must be same. So through this we can connect capital B, capital C and small a. So you can write your capital B. So this you can do as a homework. So capital B you can find as is equal to square root of h cross alpha by pi e raised to I pi by 4 divided by 2i times a, and capital C. Similarly, you can find capital C is minus root h cross alpha by pi e raised to minus I pi by 4 divided by 2i. So this is not very complicated step, so no need to do any homework for this. So this you can just try to work out. This is an exercise for you. Simple exercise, you can work it out, just equate it, and you can find the relation between B, C, and small a. So now we have got the relation between B, C, D with A. So this equation number I can put as equation number 10 and equation number 11. So we have three equations, one connecting capital D and small a, the other one are the connecting B and A and C and A. Now through this, obviously I can connect B, C, and D. Okay, so what was our the equation connecting the equation connecting A and D is this, your equation number 7, and that equation is capital. Okay, so better I will write here capital D equal square root of h cross alpha by 4 pi new capital D. Yep. Okay, so this times A. Now this is your equation number 7. We can from 10, 11, and 7, I will get the connection between the B, C, and D, and that we say the connection formula. Okay, now I can write my B is minus I e raised to I pi by 4 times capital D, and C is I e raised to minus I pi by 4 capital D. So remember, we have two regions. We have two regions on this problem. The region 1 and region 2. So WKB wave function is valid in both region. Now I can able to connect the WKB wave function 1 and 2 through this equation. So this equation numbers can be written as 12 and 13. And these equations we call is a connection formula. Now the last step is by knowing this B, C in terms of D, I can rewrite my the wave function, the WKB wave function in the region 1 and region 2. Okay, so that you can do as an exercise for you. So now from here, the WKB wave functions are say WKB of x. I can write this equal to 2D. So this you can do as a homework. 2D divided by root of p of x, the sine of 1 by h cross integral x to 0 p of x prime dx prime plus pi by 4. So this is for region 1, that is for x less than 0, and it is equal to capital T by root p of x, and by meter magnitude of p of x e raised to minus 1 by h cross integral 0 to x magnitude of p of x prime dx prime. This is for the region 2 for x greater than 0, and that is your complete the WKB wave function. So we have got this WKB wave function through this connection formula, and we have got this connection formula by using a patching wave function. Okay, so I will just summarize what are the things that we have discussed till now. Okay, so remember, WKB approximation is a powerful approximation and is usually valid if the potential is a slowly varying function, but at certain positions these wave functions are not valid. That is when, if you consider the point very near to the classical turning point. So very near to the classical turning point. So very near to the classical turning point, the WKB wave function is not valid. So there I have to know the exact wave function. But since it is the a very small region, I can expand my potential as a function of x, and by taking the first order approximation, since the potential is a slowly varying function, in the first order approximation the potential can be treated as a linear function of x. Okay, so potential can be treated as a linear function of x. So in the patching region, or in the region very near to the turning point, I can write my Schrodinger equation in a new form. That new form is known as the Airy equation. This is a form of Airy equation, and its solutions are well known. Okay, its solutions are, there are two possibilities for the solutions for when z greater than 0 and z less than 0. For z greater than 0, it is exponential, and for z less than 0, it is harmonic. Okay, so then what we have done is we have found uh, an overlap region in 1 and 2. So the overlap region are the region in which the potential is linearized. That means I can use a patching wave function and as well as WKB wave function. So the overlap region are the region in which both wave functions are valid, both WKB and patching wave function. And so with that, what we have done is we have found the constants, the coefficients of the WKB wave functions. So first we have considered the overlap region 2. So in the overlap region 2, I have found the connection between small a and capital D. And thereafter we have considered the overlap region 1. So this is our overlap region 2. I will write here. This is a region of so this is a region of overlap region 2, and the next one is this overlap region 1. Okay, so in this overlap region, the patching wave function WKB wave function must be same. So then I could able to connect the coefficients in the WKB wave function on the both regions. So I can connect B and D and C and D, and this connection is called the connection formula. And just finding the connection formula, we can find the exact form of the WKB wave function. So we can have the simplification. So if you simplify it, the WKB wave function region 1 and region 2. So this is for region 1, which is classically allowed, and this is a region 2, which is classically forbidden. Now we have got a very good connection, the WKB in wave function about the region. And with this, we have illustrated how we can connect the wave function about on the both sides of a turning point. Okay, so this is the difficult part of the WKB problem. So whenever the turning point is present, we have to use the patching wave function in order to connect the WKB wave function on either sides. Okay, so that's it. Now this can be extended to the problem with 2 turning points, 3 turning points, etc. So that is just extension of the same mathematic tricks, so that you can do it yourself. You can refer the textbook. Exactly has many such illustrations, so you can do the other exercise, other problems as the exercises. Then you'll become expert in this the WKB approximation. Okay, so hopefully I think you have got the main idea behind the WKB approximation and the connection formula. And possibly we'll have a tutorial session on this in the next lecture. So we are stopping here. So thank you everyone for watching this.